In the third part, I will introduce some key features of Elasticsearch.
Let's see the Elasticsearch cache mechanism first. Elasticsearch caches are classified into query cache, field data cache, and request cache. It caches the filter execution results contained in a query common terms. Terms and range filters are cached after certain conditions are met. It's used to cache the query result in the filter. Based on the LRU policy, which is short for the last recently used algorithm, the system automatically deletes the least recently used query cache when the cache is full. Secondly, field data cache. When aggregation, sorting, or script access is performed on a word segmentation field for the first time, the field data cache is loaded. The cache is at the segment level. When a new segment is opened, the old cache is not loaded. Instead, the field data cache corresponding to the new segment is directly loaded to the memory. Loading field data cache is an inexpensive operation. When field data is loaded to the memory, the segment corresponding to field data cache resides in the memory within its life cycle. That is, when segments are merged, the field data cache of more segments is loaded. Field data consumes most of the JVM heap memory, especially when the high radix word segmentation fields with a large number of different words after word segmentation are loaded. The aggregation and sorting of these fields are meaningless. We need to consider whether to use not analyzed instead, so that the doc values can be used for aggregation and sorting. The not analyzed function is enabled by default. Thirdly, request cache. Currently, only requests whose size is 0 are cached. Therefore, hits.total aggregations and suggestions are cached instead of hits. Request cache is very intelligent and ensures that the query results are consistent with the non-cached query results in near real-time search. By default, request cache is disabled. You need to enable it. Another mechanism supported by Elasticsearch is inverted index. The traditional search method starts from keywords and then search for specific information that meets the search criteria by keywords. That is, search for values by keywords. Elasticsearch uses inverted index to search for keys by values. In Chinese for text search, value is the keyword that we want to search. The place where all keywords are stored is called a dictionary. The key is a document number list. You can find documents with the keyword value in the document number list. Just like these figures, we don't look up the specific document number. Instead, we cut the content into pieces and just maps the keywords and find out which document had the most keywords. For example, when we hear a small part of a familiar sound but can't remember its name, we can find it by searching the lyrics of this small part instead of directly searching its name. The Elasticsearch also provides user two routine algorithms to determine into which shared we are going to store the file. Actually, the process depends on the formula. Shared is equal to hash routine % number underline of underline primary underline shareds. Routine is changeable value. The default value is a document ID. You can also set it to a customized value. Routine uses the hash function to generate a number and divides the number by the number underline of primary underline shareds to obtain the remainder. This remainder distributed between 0 and the number underline of underline primary shareds minus 1 is the location of the shard we are looking for. Besides, Elasticsearch automatically balances slices among available nodes, including adding new nodes and taking existing nodes offline. Theoretically, this is an ideal behavior. We want to promote the replica shard to recover the lost primary shard as soon as possible. We also want to ensure that resources are balanced in the entire cluster to avoid hotpots. Elasticsearch provides the following algorithms for self-balancing policies, and we won't explain them here because of the time limitation. The next one is the Elasticsearch capacity expansion. As the service volume increases, the Elasticsearch service has a large number of tasks. If the storage resources and computing capabilities of the Elasticsearch service cannot meet the service requirements, you need to expand the capacity of the Elasticsearch service. Currently, capacity expansion scenarios can be classified into the following two types: add more Elasticsearch node instances, or add nodes. That is, add more servers to the cluster. By doing that, Elasticsearch can handle the scenarios with high physical resource consumption and excessive index data. By contrast, if some Elasticsearch servers need to be brought offline or the number of used Elasticsearch servers need to be adjusted due to insufficient server resources, you need to reduce the capacity of the Elasticsearch service. Compared with capacity expansion scenarios, capacity reduction scenarios can be classified into the following two parts: reducing instances, that is, reducing Elasticsearch service instances, and the other is to remove the Elasticsearch server from the cluster. The shutdown operation may seem simple, but there are some rules as well. If you need to reduce the numbers of master instances, please ensure that the number of master instances is greater than or equal to 3, and adjust the value of minimum underline, leave underline, master underline nodes. The default value -1 is recommended. Secondly, to reduce the number of data instances to ensure that the number of replicas of all indicators is not 0, and the value of cluster underline, routine underline, allocation underline, same underline, shared underline, host is true. Thus, before capacity reduction, we should estimate the data disk usage to prevent insufficient disk space caused by data redistribution after capacity reduction. And Elasticsearch can index data stored in HBase. The figure on the right side shows the process. When Elasticsearch indexes the HBase data, the HBase data is written to HDFS, and the Elasticsearch creates the corresponding HBase index data. The index ID corresponds to the row key of the HBase data. This ensures that each index data is unique and HBase data can be searched in full text. Batch indexing are used to read all data in HBase by submitting a MapReduce task and create indexes in Elasticsearch. Elasticsearch also supports the multi-instance deployment on a node. Multiple Elasticsearch instances can be deployed on one node and differentiated from each other based on the IP address and port number. This method increases the usage of the single node CPU, memory, and disk, and improves the indexing and the search capability of Elasticsearch. According to the Elasticsearch official documents, it's not recommended that you specify a memory greater than 32 GB when deploying Elasticsearch. However, the memory capacity of a server is much larger than 32 GB. Therefore, we need to create multiple Elasticsearch instances on one server to make full use of resources. Like this figure, there are one Elasticsearch master and several Elasticsearch nodes on node 1, node 2 as well. The cluster capacity and performance depend on how Elasticsearch allocates shares on nodes. If all data flows to one or two nodes because they contain active indexes in the cluster, the nodes will display high CPU, RAM, disk, and network usage. When these nodes are extremely busy, dozens or hundreds of other nodes in the cluster may be idle. Elasticsearch uses the shared placement policy to solve this problem. We will configure the parameter cluster.routine.allocation.same_shared.host to true. Then allocate the replica to a particular node moved from one node to another like this figure. And there are some new features of Elasticsearch, and I won't explain them in details here.
Okay, these are all the contents of Elasticsearch. We have learned the basic concepts, function, application scenarios, architecture, and the key features of it. I hope you can review them after this lecture. Next time, we are going to learn Redis. Thanks, see you next time.